In this lesson, I'm going to teach you about the concept of a logarithm. I'm going to start by just telling you what a logarithm is directly, and then we'll try to unpack the definition. A logarithm undoes the action of an exponent. To explain this properly, let's try to remember what an exponent actually does. When we write 2 to the power of 3, we're saying that we start with the number 1 and we multiply it by 2 3 times, and that gives us the number 8. So if 2 to the power of 3 tells us to multiply the number 1 by 2 a total of 3 times, then the corresponding logarithm should ask the opposite question. So if we wanted to rewrite this as a logarithm, then the corresponding logarithm would be log to the base 2 of 8 equals 3. But then, a fair question is, what does this log base 2 of 8 actually mean? Well, if 2 to the power of 3 tells you to multiply 1 by 2 3 times, then log base 2 of 8 is asking the opposite question. How many times can I divide 8 by the number 2 to get to the number 1? So in this sense, the log base 2 of 8 really is the opposite of 2 to the power of 3. Where 2 to the power of 3 is going to ask you what happens after multiplying, the log base 2 of 8 asks you what happens after you divide instead. And the answer being 3 also makes a lot of sense. If you start with the number 8 and then divide it by 2, well, you end up with the number 4. If you then divide that by 2, you'll end up with the number 2, and if you divide by 2 again, you end up with 1. Since this takes 3 turns, log base 2 of 8 is the same thing as 3. Now because of this opposite relationship between these two, it makes sense that the numbers 2, 3, and 8 appear in both of these expressions. So these two over here are actually sometimes floated around as an alternative notation for 2 to the power of 3 and the log base 2 of 8. So for example, an exponential like 2 to the power of 3 can be written like this, where you know 2 and you know 3, but you're trying to find the missing number, which of course is going to be the number 8, because 2 to the power of 3 is equal to this 8. But for a logarithm, you know the 2 and you know the 8, but you're missing the exponent up here. So the way you actually find the exponent is by dividing this 8 by 2 repeatedly until you end up with the number 1. So then of course, the log base 2 of 8 is going to be the same thing as the number 3, so the exponent is the missing number. Now despite the fact that this notation might be easier for you to understand, this is actually the notation you're always going to see, so you should probably learn this one for now. Maybe in some time people will switch to this one, but for now this is definitely the dominant notation. That is a bit of a shame because this one is so much easier to understand, but historically people have been using this for so long that you should probably learn to do it as well. But of course you can always imagine it like this anyway. So now that we roughly understand what logarithms are, I want to show you that logarithms actually cancel exponentials. So let me start with this expression over here for just a moment. So we know that 2 to the power of 3 is the exact same thing as the number 8. But we also know that this number 3 is the same thing as the log base 2 of 8. So I should be able to replace this 3 for the log base 2 of 8. So at this point, we've actually arrived at our first important formula. We can see that 2 to the power of the log base 2 of 8 is going to be the exact same thing as the number 8. So in a sense, a 2 and a log base 2 cross each other out to just leave you with the number 8. However, there's absolutely nothing special about the number 2 or the number 8. Rather than starting with 2 to the power of 3, you could have started with any integer to the power of any integer you liked, and you could have repeated these exact same steps, and you would have always noticed that this base crossed out with the log base of whatever you had. So because of this, I'm going to replace the 2's for a's, and I'm going to replace the 8's for b's. So anytime we have anything in this form, where you have a to the power of log a of b, where a and b can be any number you like, you can just cross out the a with the log a, and you just be left with the number b. But rather than starting on the left and working towards the right, you're going to notice that the same is true if we start on the right and work to the left as well. So if we know that the log base 2 of 8 is going to be the same thing as 3, then we also know that 8 is the same thing as 2 to the power of 3, so we can replace this 8 for 2 to the power of 3. So this just shows us that the log base 2 of 2 to the power of 3 is the same thing as the number 3. So a log with a base of 2 crosses out with an exponent of the base of 2 as well. Now again, since there's nothing special about the 2 or the 3 here, I'll just go ahead and replace the 2 for the a as I did before, but I'll replace the 3 for a c. So at this point we can see that the log base a of a to the power of c is the same thing as c. So no matter whether you have the a to the power of first, or you have the log base a first, a log base a always cancels with a to the power of anything. So this just tells us that logarithms cancel out exponentials. Now these two expressions are actually really important, because they always allow you to rewrite an exponential like this in terms of a logarithm. And that's actually incredibly useful, because anytime you can't calculate the exponential, you may actually be able to calculate the logarithm. Let me actually show you this with an example. So for example, suppose we wanted to find the value of x in this expression over here, where 3 equals 4 to the power of x. The first step is going to be to rewrite this as a logarithm, and then we can directly find the value of x using a calculator. Now in order to actually get the x on its own, I'm going to take the log base 4 of both sides. Once I do that, I can just cross the log base 4 with the 4, and then I'll be left with the x on its own, as you can see over here. So as you probably already know, if you start off with a true expression, then you can apply some operation to both sides and the expression must remain true. So it's perfectly okay to take the log base 4 of both sides. But the reason we did that is we can see that the log base 4 will just cross out this 4, as you can see in this expression, and we'll just be left with the x on the right hand side. And I also usually like to have variables on the left hand side, so let me actually swap the left and the right. So we can see that x is just going to be the same thing as the log base 4 of 3. And the log base 4 of 3 is something you can just type directly into a calculator. Now there are many calculators out there that don't actually allow you to type the log base 4 of 3 directly like this. If you have a calculator like that, you can also type it like this. In a future lesson, I'll explain to you why the log base 4 of 3 is the same thing as the log base of 3 divided by the log base of 4. But you can just type the log base of 3 divided by the log base of 4, and that's going to be the same thing as typing log 4 of 3. But in either case, we see that the missing value, this x here, or the log base 4 of 3, is the same thing as 0.79248. And if you think about that for a moment, it actually does make some sense. We're asking, what power do you raise 4 to in order to get the number 3? Well, if you raised 4 to the power of 0, you'd get 1. And if you raised 4 to the power of 1, you'd get 4. So it makes sense that the answer is somewhere between 0 and 1. There is another equivalent way to think about this instead of taking the log base 4 of both sides. And there's a little animation that I'd like to show you to explain it. If we take 3 equals 4 to the power of x, we can copy it down here one more time, and I'll show you how we can get to this line. If you want to get from 3 equals 4 to the power of x directly to x equals log base 4 of 3, you can just imagine this animation. I want you to think about this 4 coming down and going below the 3, and then you'd acquire a log on the left hand side. So either way, we still find that the log base 4 of 3 is still equal to x, just as we found over here. So to be clear, you don't really need to write this step out. It's quite good to do so, but you don't need to. You can always just imagine bringing the 4 below the 3 and writing a log on the other side. But that just about completes the example that I wanted to show you. So let's say a few more things about logs before I end this lesson. So the first thing I want to say is that any expression that can be written as an exponent can also be rewritten as a log. So if we started with a to the power of c is equal to b, then we can just take this a, move it below the b, and then just take the log of the right hand side. Remember, that's the same thing as taking the log base a of both sides. So the idea is that anytime you write a to the power of c is equal to b, you can always rewrite this as c equals the log base a of b. These two expressions are completely equivalent. Now, given this information, this has some direct implications. So let's look at some particular examples first. So the first implication comes from realizing that a to the power of 1 is just equal to a. And if this is the case, then we can bring this a below this a to just write the log base a of a equals 1. And I'd prefer the constant 1 on the right hand side, So I'm just going to swap these two sides. So we're saying that if you pick the exact same a for both of these, then the log base a of a has to be equal to the number 1, no matter what. I can just demonstrate this with an example quite easily. If we have the log base 7 of 7, that's just asking us, how many times can I divide this number 7 by 7 to get the number 1? Well, obviously the answer is just 1. So the log base 7 of 7 must just be 1. So the next implication comes from realizing that a to the power of 0 is just always equal to 1. Except for the situation when a is equal to 0, but we don't talk about the root of all evil here. But then, if that's the case, then if I bring this a below this 1, then we can say that the log base a of 1 always has to equal the number 0. But just like before, I'm also going to put the log on the left-hand side. So if a to the power of 0 is going to equal 1, then we can always say that the log base a of 1 must always be equal to the number 0. This is also quite easy to justify with an example. So if we have the log base 12 of 1, we're asking how many times do we need to divide 1 by 12 to get the number 1? Well, we already have the number 1, so we don't need to divide the number 1 by 12. So since we need to divide the number 1 0 times to get to the number 1, then the log base 12 of 1 must be the same thing as the number 0. Now at this point, I hope you roughly understand what logarithms actually are, but there is actually a convention that I need to tell you about, so let me write it down very quickly. So what I've written here is that most of the time, when you see logarithms in the wild, you'll probably see them written without a base. If this is the case, then by convention, we assume that log is the same thing as the log base of 10, and this ln over here is the same thing as log to the base of e. However, depending on what you're actually reading, you might actually see some authors that use log to mean the log base e, or even the log base 2 or something else. In general, whenever you're in doubt, it's always better to actually write the base, but if you're reading something and you can't actually see a base, it's probably good to assume that this is the convention that's probably being followed. This is by no means a universal convention, and people will disagree on this, but most of the time you will see log written as log 10, and ln is almost always the log base of e. Now in a follow-up lesson to this one, I'll explain to you why the log base 10 is so important, but then, later on, you'll start to see why ln is so important. In a sense, ln is probably the most important logarithm of all of them. But I'm sure you'll see that as you study more and more mathematics. So at this point, I'd just like to summarize the lesson. In this lesson, I introduced the idea of a logarithm to you. I explained that 2 to the power of 3 tells us to start with the number 1 and multiply it by 2 3 times. But the log base 2 of 8 tells us to start with the number 8 and then divide it by 2 until we get to 1, and then we keep note of how many times we needed to divide by 2. So if exponentials are asking what I get if I raise 2 to the power of 3, then logarithms are asking what I actually needed to raise 2 to the power of to get the number 8. By interpreting this result carefully, this told us that we can cross exponentials and logarithms out directly. And this is a really useful result because it allowed us to show that if a to the power of c equals b, then c must always equal the log a of b. Then by directly interpreting this result, we were able to show that the log base a of a must always equal 1, and the log base a of 1 must always equal the number 0. And then we explained that sometimes, by convention, you won't actually see the base written. Whenever that happens, you should assume that log means the log base of 10 and ln means the log base of e. Now logarithms are a standard part of the mathematical toolbox, and if you continue studying maths, there's no way that this is going to be the last time that you see them. In this lesson, I spent most of the time explaining what logarithms are, and I spent very little time explaining why they're useful. In a follow-up lesson to this one, I'm going to talk about the idea of a logarithmic scale, and when you understand it, you'll see why logarithms are so useful. Also, aside from these very simple rules that we're able to derive by looking at 2 to the power of 3 equals 8, there are quite a few more rules that you can also derive as well. Most of the other rules actually come from starting with an index law and then converting them into a logarithm. But at this point, I think you've been sufficiently introduced to logarithms, so I think I'm going to end this lesson there. So you should join me next time where we talk about logarithmic scales. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.